Hello everyone, thanks for your interest in CollaboVR, a reconfigurable framework for creative collaboration in virtual reality. This is Zhenyi He. I'm a 6-year PhD student in Virtual Reality Lab at New York University. The project CollaboVR has been done in collaboration with Ruofei Du from Google and my advisor, Professor Kemperlin. Communication is happening every day and everywhere, locally, remotely. However, it is not always very effective. For example, sometimes we need to sketch on whiteboards for better clarity, but someone's line of sight may be blocked. In another case, people in conventional video conferences can hardly read pointing gestures to digital contents easily. We realize that sketching, one of the most natural and fun ways to express ourselves, has rarely been explored in collaborative VR. Additionally, it is an open question what is the best layout and interactive mode for creative collaboration. We investigate the following research questions. What if we could bring sketching to real-time collaboration in virtual reality? If we can convert raw sketches into interactive animations, will it improve the performance of remote collaboration? Are there better user arrangements and input modes for different use cases? Or is it more a question of personal preferences? To answer the questions, we present CollaboVR, an open-source reconfigurable framework for both co-located and geographically dispersed multi-user communication in VR. Our system unleashes users' creativity by sharing freehand drawings, converting 2D sketches into 3D models, and generating procedure animations in real time. To minimize the computational expense for VR clients and offering a reconfigurable framework, we leverage a cloud architecture in which the computational expensive application ChalkTalk is hosted directly on the servers, with the results being simultaneously streamed to clients. For each frame, CollaboVR servers transmits users' strokes to Cloud App, broadcasts the rendering results from ChalkTalk, and sends audio streams to all clients simultaneously. To adapt different use cases and optimize the virtual spaces depending on tasks, we further support the real-time switching of different use layouts. Before we came up with the layout conditions in detail, we explored the variety of user arrangements and input modes that affect communication and collaboration. We investigate 3 user arrangements and 2 input modes. The first one is side-by-side. The side-by-side arrangement places each remote users in a shared virtual space, which is defined within the tracking range of the headset. All users may focus on the contents during the creative collaboration. However, the avatars of 2 users may be occluded with each other like in real life. The face-to-face arrangement solves the occlusion issue by mirroring all the other avatars' locations to the side of their currently activated interactive board. See the example that user 1 enables the face-to-face arrangement, so user 2 in user 1's view is mirrored to the other side of the left interactive board, which user 2 is looking at. Hence, user 2 and user 1 did not visually block each other. Then, let's take a look at the gaze interaction. Spot A is defined as the intersection point of the gaze direction between 2 users and the left interactive board. Assuming that user 1 and user 2 are both looking at spot A, before mirroring operation, user 1 and user 2 are only aware of themselves looking at spot A. After the mirror operation, the gaze direction between users and the content is maintained. Moreover, users are aware of each other's focus when gazing at spot A at the same time. Since we did not manipulate the content in CollaboVR, the content is still readable and correct to each viewer. Besides, this user arrangement is also easy to scale. Here shows the extended version with 4 users from user 1's perspective. Each user sees the other mirror reverse through their respective boards. The respective board is decided based on their corresponding users' facing direction. Compared to the side-by-side arrangement, our face-to-face arrangement reduces visual clutter while maintaining eye contact. The hybrid arrangement inherits the teaching in a classroom metaphor, where the teacher uses the face-to-face arrangement to observe the students, and the students use the side-by-side arrangement for classmates and the face-to-face arrangement for the teacher. We envision that this arrangement may be useful for online education with a large audience. Regarding input modes, we explore two of them in CollaboVR. One is direct mode, which adapts the metaphor of writing on a whiteboard. The second one is projection mode, which enables the user to sketch on a private workspace at hand and project the contents onto the shared interactive board. Combining the real-world metaphors, we design three layout conditions to evaluate the CollaboVR system: integrated, mirrored, and projective layouts. The integrated layout inherits the side-by-side whiteboard metaphor by applying side-by-side user arrangement and direct input mode. This layout places remote or co-located participants into the same shared virtual space. The mirrored layout inherits the face-to-face communication metaphor. This layout resolves issues with clutter and occlusion by flipping other avatars to the opposite side of the interactive board. The projective layout inherits the lecture with a presentation metaphor. The presenter can focus on sketching or designing their private workspace and project the content to the shared interactive board for the other audience. To evaluate CollaboVR, we conduct a within-subject user study with 12 participants. Our findings reveal that users appreciate the custom configurations and real-time interaction in CollaboVR. After running repeated measure ANOVA on the data collected, we found that CollaboVR can foster communication and help collaboration when participants are geographically dispersed. The mirrored layout had better usability and task performance, and received the highest ratings from the participants. Below are the takeaways of our project. First of all, we developed CollaboVR, a reconfigurable end-to-end collaboration system using a cloud-based computing architecture to support multi-user sketch, audio communication, and collaboration in 3D. Secondly, we designed custom configurations for real-time user arrangement and input modes inspired by real-world metaphors. Also, we provided quantitative and qualitative evaluation of CollaboVR with 12 participants to discuss its advantages, limitations, potential impacts on collaborative VR systems. Lastly, we will open source our software to facilitate future development in collaborative VR systems with multimodal inputs. Next, we showcase several live demos of CollaboVR. CollaboVR can be used for trip scheduling. Multiple remote users are rendered as virtual avatars in front of a large virtual interactive board. With freehand drawing, users can write and draw their desired travel plans and coordinate with friends via both audio communication and sketches. CollaboVR can also be helpful for interactive presentations. The presenter and the audience are on the opposite side of the interactive board, while the sketches are shown identical to both of the audience and the presenter, while maintaining the gaze interaction. CollaboVR can further help with designing spatial layouts, especially in 3D. The user can draw furniture with a combination of primitive 3D objects and place them directly at the preferred locations. The system functions the same for left-hand users and right-hand users. All the drawings can be further manipulated after draw. Moreover, CollaboVR provides users with notepad tabletop writing experience. The designer can focus on sketching the concept on a private interactive board. The experience is close to drawing on a digital tablet with a pen, while the contents will be projected to the large shared interactive board to the other audience. We envision CollaboVR may facilitate future research in collaborative work in virtual reality. Thank you very much.